In 1907, Albert Einstein had what he described as his happiest thought. He realized that gravitational acceleration was indistinguishable from any other form of acceleration. To understand why this would make him so happy, we must first understand the problem that he was trying to solve. Because ultimately, the equivalence principle isn't just about gravity, it's about cause and effect. An object moving with uniform velocity feels no motion. We judge motion relative to our surroundings. Imagine three people floating through empty space at different speeds. All three can claim that they are not moving, and that the other two are moving in relation to them. What we say in this scenario is that there is no preferred reference frame. No perspective can claim to have privileged information about the state of the system, and this fact is described by Galilean relativity. Maxwell's equations of electromagnetism, however, complicated this picture. For these equations to function, each observer must measure the speed of light to be the same value, relative to their own reference frame, contradicting Galilean relativity, at least when it comes to the speed of light. This is the contradiction that Einstein resolved with his theory of special relativity. The first postulate of special relativity states that the laws of physics are the same in all inertial reference frames. What Maxwell's equations tell us is that the speed of light must be invariant for the laws of physics to remain the same for all observers, so the second postulate logically follows from the first. The second postulate states that the speed of light in a vacuum has the same value for all inertial reference frames, regardless of the motion of the observer. Many questions arose out of special relativity. Einstein's solutions seem to create a series of very confusing, paradoxical thought experiments. Perhaps unsurprisingly, overturning the fundamental basis of Newtonian physics had a number of unintended consequences. The central problem that Einstein was attempting to solve persisted. How do you describe a physical system without giving preference to any reference frame? Absolute notions of space and time were the backdrop for Newtonian physics, and this made describing the unchanging laws of physics simple. But in the truly relativistic universe, where space and time appear to depend on your own perspective, where there is no preferred reference frame, we needed a radically new method for describing the laws of physics. The equivalence principle was the answer. This principle states that gravity is equivalent to all other forms of motion, but perhaps more generally, it makes all forms of motion equivalent. Absolute space and time, which underpinned the unchanging laws of physics, were replaced by absolute motion. And the method that Einstein used to describe this absolute motion was the Minkowski metric. A metric is a mathematical tool used to determine how to calculate the distance between 2 points. If you want to calculate the length of a line on a sheet of paper, you need a metric that has an x and y. Pythagoras' theorem does the rest, and we can use calculus to link distance, velocity, and acceleration. After coming to grips with the theory of special relativity, Einstein's math teacher, Hermann Minkowski, realized that the metric used to determine the distance between 2 points in spacetime would need x, y, z, and time. But time needed to have the opposite sign from the spatial axes. The reason for this comes down to a concept called Lorentz symmetry, which is sometimes called Lorentz covariance. If two people are observing each other, relativity demands that their perspectives are symmetric. To illustrate this, I'm going to derive the time dilation formula from special relativity, but I'm going to cheat just a little bit by using a conclusion and working my way backwards. That conclusion is that all objects move in 4 dimensions at the speed of light. We start with a metric that has x, y, and z, and we add time, but I'm going to use the Greek letter tau instead of t. The speed of light functions to convert length into time, so I add that, then square each dimension to satisfy Pythagoras' theorem. I'm not looking for distances. I'm looking for a velocity, so I add d to signify that these are changes in distance. Tau is the time coordinate of the observed reference frame, but the observer can't measure that value. So, to convert these values to velocity, I divide the changes in distance by the time the observer is recording. We can now replace the x, y, and z with v for velocity. We move v to the left side, divide both sides by the square of the speed of light, simplify, and square root both sides. And now we define a new term, gamma, to equal this result. And here we have the time dilation formula. It shows that the change in proper time of the observed reference frame trends to zero as the speed of the reference frame approaches the speed of light. But this is not how this formula is normally presented. Usually, it is written this way, so that the change in t, which is the time the observer is recording, trends to infinity as the speed of the observed reference frame approaches the speed of light. So, just to recap, x, y, and z represent the observed velocity of the reference frame that is being measured, and t is the observer's clock. Tau is the clock value of the observed reference frame, but this value is not measurable, not by the observer, not even from inside the observed reference frame. The reason for this is because the clocks inside the observed reference frame run at that speed. So when it changes, the clocks change with it. So no change in the value of tau can be observed from that perspective, which means that this metric is unusable. The Minkowski metric exploits Lorentz symmetry to create a usable one. From the perspective of the observed reference frame, the observer is the one who is moving, but in the opposite direction. So we can deduce that from their perspective, our x, y, and z values are simply the opposite of what we have measured of them. This creates what are known as the mostly pluses and mostly minuses convention, both of which are mathematically equivalent, and they result in an invariant time interval that allows us to make objective statements about the relationship between these two reference frames, despite not being able to establish any preferred reference frame. General relativity describes gravity as the curvature of spacetime, but even in so-called flat spacetime where gravity is not present, this metric already results in some very strange geometry. Since the time axis has the opposite sign from the spatial axes, the shortest distance between 2 points requires the longest amount of time to traverse. This results in a thread-like structure. The universe is depicted as a tapestry, with every particle having its own continuity of time. This is the natural result of resolving the contradiction between Maxwell's equations and the concepts of absolute space and time, while being unable to determine a preferred reference frame. The fact that time dilation is an observer-dependent mechanism is what has resulted in this reversal. Proper time contracts, it does not dilate. But working within that perspective creates issues. Proper time is invariant to the observer. As it contracts, your own perceptions of time contract with it. Your conscious rate of change is equivalent to your own proper time. So this is not the definitive solution. The fact that this description does not match our ever-present observations of the universe is the first hint that something about this picture is incorrect. Prior to Minkowski developing his metric, Henri Poincaré demonstrated that the Lorentz transformations that underpin relativity could be expressed in 4 dimensions using the imaginary unit. The imaginary unit is a mathematical concept which provides the basis for complex numbers, which are a coordinate system. This coordinate system resembles Cartesian coordinates in the respect that they can be placed on a grid, and when adding them together, they still function just like Cartesian coordinates. However, when multiplying complex numbers, they function closer to polar coordinates, making them a kind of hybrid coordinate system. The metric Poincaré developed is now known as imaginary time, and it is used in thermal field theory, which relates quantum field theory to statistical mechanics. The primary claim of equivalent time theory is that the Dirac equation disproves the existence of Minkowski spacetime, and while Minkowski's solution is extremely useful, imaginary time is most likely the correct metric. The Wick rotation, which converts the Minkowski metric into imaginary time, undoes the reversal which Minkowski imposes on the system. The shortest distance between 2 points becomes the shortest once again. I think that the time interval of particles traveling at the speed of light is most likely what has prevented this metric from being considered real, as from this perspective, a photon has a proper time value of 0. In standard relativity, a photon's time interval is judged to be infinity, which I assert is an unphysical result. I've been calling this the original sin of relativity, as it is the first of many infinities that the theory produces. The photon's proper time value should be considered evidence that time is not a dimension. Our perception of time emerges from the relative density of periodic synchronization events, and ultimately, time is a property of all dimensions, not just one. Imaginary time is an unfortunate name for the metric, as it is neither imaginary nor is it time. But the evidence strongly suggests that spacetime has three macroscopic dimensions and a Planck scale complex phase, while the equivalence principle still holds as the best description of how causes relate to effect. Thank you.